Welcome to ZorgAI Paper, the podcast where we explore the most relevant AI research papers and break them down for the medical and healthcare community and for curious minds everywhere. I'm your host, Morteza, and this episode kicks off our deep dive into one of the most talked about models in computer vision, segment anything, developed by Meta AI. Joining me is Zora, my AI co-host, who will help highlight key points and ask questions you might have as you listen. Zora?
Hi everyone, I'm Zora, your AI companion. I'll be asking questions along the way, especially when we hit technical or novel ideas that might need some extra explanation.
So let's start with the big idea. The paper explores how can we build a zero-shot or promptable segmentation model. It means a model that doesn't need retraining every time you want it to do something new. Instead, you give it a prompt, a hint about what you want to segment, and it figures out.
Hold on. Zero shot and promptable sound a bit technical. Can you explain what these terms mean in simple terms?
Absolutely. Zero shot means the model can handle a task it hasn't seen during training. Imagine showing it a type of image it's never worked on and it still performs well. Promptable means we can guide the model using simple input like points, boxes, or even text, a bit like giving it instructions.
So it's kind of like giving the model a nudge instead of a whole new training session.
Exactly. And here is where it gets interesting. Unlike traditional segmentation models that are trained for specific tasks, this one separates the image processing from prompt interpretation.
Why does that matter? What's the advantage of separating image and prompt embeddings?
Actually, it makes the system fast. The image embedding, the heavy lifting part, is done once. After that, you can apply many different prompts without reprocessing the image. That's useful in real-time setting, like interactive tools or diagnostics.
The paper also mentions it's ambiguity aware. That sounds important. What does that mean?
Good question, Zora. It means the model knows there might be more than one right answer, so it gives multiple segmentation options per prompt, along with confidence scores for each. This is helpful in case where the object's boundaries aren't clear.
How did they train the model to be that flexible?
They did it with a clever pipeline called a data engine made of three steps. First step is called assisted manual labeling. Human annotators use an initial model and refine segmentations with click and brush tools. They created 4.3 million masks across 120,000 images. The second step is semi-automatic. The model proposed masks and humans corrected them. They ended up with 5.9 million masks from 180,000 images. And the last step is fully automatic. The model predicted masks on 11 million images. After filtering for quality and removing duplicates, they created a massive dataset of 1.1 billion masks called SA1B.
Wait, 1.1 billion? That's a huge number. Why is this scale such a big deal?
Great question. Data is the foundation of any AI model. With this volume and diversity, the model learns to generalize. It becomes capable of understanding a wide variety of object types and visual cues, crucial for applying the model in new domains.
And the architecture itself, what kind of backbone did they use?
They used a vision transformer, pre-trained using MAE or mask autoencoder. This method trains the model to reconstruct missing parts of an image, making it more robust and efficient. Up to 75% of image patches are masked during training.
What exactly is a vision transformer, and why is May important?
A vision transformer, or VIT, treats images like sequence of patches, just like how language models process words. MAE teaches the model to fill in missing visual information, which makes it better at understanding images even with partial information.
How do they handle the different prompt types?
They encode each type of input differently to capture distinct semantic and spatial information. Points are represented using both their spatial coordinates and an associated label, like foreground and background. They are embedded using learned positional encoding to indicate their location within the image grid. Boxes are encoded by embedding the coordinates of their top left and bottom right corners, and text processed using the clip model, which transforms the text prompt into dense embedding that aligns with visual feature in the image. This allows semantic guidance based on natural language descriptions. All these embeddings are projected into a common latent space and merged using element-wise summation. This unified representation is then passed into a transformer-based decoder, which incorporates an output token to guide the generation of the final segmentation mask conditioned on the combined input signals.
That output token part sounds like something from NLP. Why is it used here?
Exactly, it's inspired by NLP models. The output token gathered information from the rest of prompts via self-attention, much like a summary token. This is used to produce final segmentation mask.
And the decoder itself, what kind of architecture did they go with?
They designed a lightweight transformer-based decoder. It uses self-attention within the prompt and two cross-attention layers, one from image to prompt and one the other way around. This balances performance with speed.
How do they measure performance?
They used mean IOU score or intersection over union across 23 datasets. One key setup was to use a single point in the center of an object as a prompt.
And how did it compare to other models?
With that single point, segment anything model outperformed the RITM model in 16 out of 23 datasets, but for multiple points, simple click model often performed better. They also tried zero-shot tasks like edge detection or object proposal or instance segmentation or even text prompted segmentation, but they didn't perform well in other tasks.
So even though it's called segment anything, it doesn't segment everything equally well?
Exactly. The generality is promising but not perfect. In particular, small or fine detailed structures remain challenging, which is important in areas like medical imaging. Let's pause here. In the next episode, we will take a critical look at the methods and results of this paper.
Thanks for explaining all those details. Looking forward to the second part of this episode.
See you next time!